Welcome! In this session, we'll tackle an exciting problem titled Longest Word with All Prefixes. We'll explore different approaches to solve it, including a brute force method. Let's dive in and sharpen our problem-solving skills together. In this problem, we are given an array of strings called words. Each string in the array consists of only lowercase English letters. Our goal is to find the longest word in this list that satisfies a specific condition. The condition is that every prefix of the word must also be present in the word's array. For instance, if the word is apple, then all of its prefixes a, ap, app, appl, and apple must exist in the array. If multiple words satisfy this condition and are of the same length, we will return the lexicographically smallest word. The input consists of a list of strings, and the output will be a single string representing the longest valid word. The constraints are important here. The list can have up to 100,000 words, and each word can be up to 30 characters long. Keeping these constraints in mind, we need to develop an efficient solution. Let's look at an example to understand the problem better. Suppose the input is words equals k, key, kin, king, kinged, kingdo, kingdom. The output for this input is kingdom. Why? Because kingdom is the longest word in the list where all its prefixes k, key, kin, king, kinged, kingdo, and kingdom are also present in the array. This satisfies the condition of being a valid word. Since no other word in the list is longer than kingdom and satisfies the prefix condition, it is the answer. Now consider another example where the input is words equals a, banana, app, appl, ap, apply, apple. In this case, the output is apple. Why not apply? Both apple and apply have all their prefixes present in the list, but apple is lexicographically smaller than apply. Therefore, apple is the correct result. Another example is words equals w, wo, war, whirl, world, word. Here, the output is world. All its prefixes w, wo, war, whirl, and world exist in the list. Although word also satisfies the prefix condition, world is longer, so it is the answer. Let's also consider the constraints and edge cases. Each word in the list has a maximum length of 30 characters, and the list can contain up to 100,000 words. This means we need to ensure our solution is efficient. For edge cases, if there's only one word in the list, we need to check if it satisfies the prefix condition. For example, if words equals a, the output would be a. But if words equals abc, the output would be an empty string because the prefixes a and ab are missing. If no word satisfies the prefix condition, we return an empty string, as in words equals abcd, xyz. Lastly, if there are multiple valid words of the same length, we return the lexicographically smallest one. For instance, with words equals abc, abd, ahub, the output is abc because it is smaller than abd and satisfies all conditions. To tackle this problem, we first consider a brute force approach. The intuition here is straightforward. We check every word in the input list to see if it satisfies the given condition, which is that all of its prefixes must also exist in the list. For instance, given the word apple, we would generate its prefixes a, ap, app, and appl and verify that each one is present in the list. The steps involve iterating through each word, generating its prefixes, and performing a lookup for each prefix. While this approach is simple to understand, its inefficiency becomes clear when analyzing its complexity. Generating prefixes for a word requires time proportional to its length, and checking for the existence of each prefix in the list involves a linear search, which can be slow for large lists. Combining these operations for all words results in a time complexity of approximately O and asterisk k squared, where n is the number of words and k is their average length. This inefficiency is particularly problematic when dealing with the constraints of this problem, where we might have up to 10,000 words with lengths of up to 30. The repeated prefix lookups and the quadratic growth in complexity make this approach impractical for large inputs. A more efficient solution is to use a tree, or prefix tree, which is specifically designed for problems involving prefixes. The key insight here is that a tree inherently organizes words by their prefixes during insertion, making it an excellent fit for this problem. The process begins by building a tree from the input words. As we insert each word, we can track whether it is complete, meaning that all its prefixes are valid. Once the tree is constructed, we perform a depth-first search, or DFS, to traverse the tree and identify the longest valid word. During the traversal, we maintain the current path and ensure that all encountered prefixes are marked as complete. If they are, we can update our result with the longest word, breaking ties lexicographically. This approach drastically reduces the computational overhead compared to brute force. Building the tree requires O(n*k) time, and the DFS traversal of the tree also takes O(n*k), leading to an overall time complexity of O(n*k). This makes the tree-based solution much more scalable for large inputs. The tree-based approach offers several advantages. First, it enables efficient prefix checks, reducing the time complexity of each check to O(1). Second, by organizing words hierarchically, it avoids redundant computations that occur in the brute force method. These features make the tree well-suited for handling the problem's constraints, such as large input sizes. However, this approach comes with some trade-offs. It uses more memory due to the additional data structures required for the tree, and the implementation is more complex than brute force. Despite these drawbacks, the tree-based approach is the clear choice for this problem. Its efficiency in processing large inputs and its natural alignment with prefix-based operations make it superior. The realization that a tree not only allows quick prefix validation but also simplifies lexicographical comparisons during DFS was the breakthrough. While the brute force method is simpler conceptually, its inefficiency under maximum constraints makes it unsuitable. The tree strikes the right balance between performance and correctness, ensuring we can solve the problem within the given limits while accepting the trade-off of higher memory usage for significantly better runtime efficiency. To solve this problem, we are tasked with finding the longest word in a list such that every prefix of the word also exists in the list. If there are multiple words that meet this condition, we need to return the lexicographically smallest one. The first step in our algorithm is to parse the input. We'll take the given list of words, for example, app, apple, ap, apply, and sort them in lexicographical order. This ensures that shorter words and words that are alphabetically smaller come first, which will help us resolve ties later on. Next, we store all these words in a set data structure. Using a set allows us to check for the existence of any word or prefix in constant time, making it much faster to validate prefixes as we process each word. For instance, once the words are stored, we can quickly verify whether AP exists in the set while validating the word apple. These preparatory steps lay the foundation for the subsequent stages of the algorithm. After preparing the input, we initialize our state variables. Specifically, we need a variable called longest_word to keep track of the longest valid word found so far. Initially, this is just an empty string. Then, we begin iterating over each word in the sorted list. For every word, we check if all its prefixes exist in the set. A prefix is any substring starting from the first character of the word up to a certain length. For example, the prefixes of apple are ap, app, and appl. To validate a word, we generate all its prefixes and check whether each one exists in the set. If we find any missing prefix, we can immediately mark the word as invalid and stop further checks. If the word passes the validation, we then compare it to the current longest_word. If the word is longer, we update longest_word. If the lengths are the same but the new word is lexicographically smaller, we also update longest_word to this word. This ensures that we always maintain the correct result as we iterate through the list. Once all the words have been processed, the longest_word variable will contain the desired result, which we then return as the output. Now, let's highlight some key insights from this approach. First, sorting the list in lexicographical order is crucial because it ensures that smaller words or ties are naturally prioritized. This simplifies the validation process and guarantees that we find the lexicographically smallest word when multiple valid candidates exist. Second, using a set for prefix validation is a highly efficient choice, as it allows us to check the existence of a word or prefix in constant time. This efficiency is important because we need to validate prefixes for potentially every word in the list. Lastly, the algorithm is optimized by stopping early during prefix validation. If any prefix is missing, we immediately discard the word, avoiding unnecessary computations. This combination of sorting, fast lookups, and early stopping makes the approach both effective and efficient.
Let's analyze the time and space complexity of this algorithm. First, the time complexity. Sorting the list takes n log n, where n is the number of words in the list. Validating the prefixes for each word involves generating its prefixes, which takes l time per word, where l is the average length of the words. Since we process all n words, the total validation cost is n asterisk l. Combining these, the overall time complexity is n log n plus n asterisk l. For space complexity, we use a set to store the words, which requires n space. Additionally, we temporarily generate prefixes while validating a word, which takes l space. Therefore, the total space complexity is n plus l. Overall, this algorithm is efficient and scales well even with larger inputs. Now let's walk through an example to see the algorithm in action. Consider the input words equals app, apple, ap, apply. First, we sort the words lexicographically, resulting in ap, app, apple, apply. Next, we process each word one by one. Starting with we find that its only prefix, exists in the set, so it is valid. We update longest underscore word to Then, we process ap. Both its prefixes, and ap, exist in the set, so it is also valid. This updates longest underscore word to ap. Moving on to app, we confirm that all its prefixes, ap, and app, exist in the set, making it valid as well. Therefore, we update longest underscore word to app. When we process apple, we validate that all its prefixes, ap, app, and appl, exist in the set. This makes apple the longest valid word so far, so we update longest underscore word to apple. Finally, we process the word apply. All its prefixes, ap, app, and appl, exist in the set, so it is valid. However, since apply is the same length as apple but not lexicographically smaller, we do not update longest underscore word. After finishing the iteration, the value of longest underscore word remains apple. Thus, the output of the algorithm is apple, which satisfies the condition of being the longest word with all its prefixes present in the list. This example demonstrates how the algorithm efficiently finds the correct result by leveraging sorting, prefix validation, and lexicographical comparisons. This implementation solves LeetCode problem number 1858, longest word with all prefixes. We start by creating a set of all input words to enable fast membership checks. We then sort the word list by length, ascending, and lexicographically for ties, which guarantees we process shorter or lexicographically smaller words first. The algorithm iterates through each word in the sorted list. For each word, we check if all prefixes of the word, from index 1 up to the full word, are present in the word set. If so, we compare it with the current longest word found. If the current word is longer than the previous longest or lexicographically smaller in case of a tie, we update the result. Finally, the function returns the resulting longest word. This approach ensures correctness while maintaining efficient performance. The time complexity is n*k, where n is the number of words, and k is the average length of words, as we process each word's prefixes. Here, we begin by importing the necessary libraries and defining our solution class. Inside the longest word method, the input is an array of strings, each representing a potential word. To make prefix lookups efficient, we first convert this array into a hash set called wordset. A hash set allows for constant time lookups, which is crucial for this problem. Next, we sort the words array. The sorting is done primarily by length, ensuring shorter words come first. If two words have the same length, we then sort them lexicographically, which means alphabetically. This ensures that if there's a tie between words of the same length, the alphabetically smaller word will take precedence. After sorting, we declare a variable longest word, which will store the result as we iterate through the words. Now, we start a loop to process each word. For each word, we initialize a Boolean flag called allPrefixesExist, which will help us determine if all prefixes of the current word are present in the set. Within this loop, we use a nested loop to check every prefix of the current word, starting from the first character up to one less than its full length. If any prefix is missing from the set, we set the flag to false and break out of the inner loop. If all prefixes of the current word exist,
we proceed to check if this word is both valid and longer than the current longest word. If it is, we update longest word to the current word. This ensures that we always keep track of the longest valid word found so far. After the loop has processed all the words, we return longest word as the final result. This implementation ensures that we efficiently find the longest word where all prefixes are present, by leveraging the hash set for quick lookups and sorting to prioritize shorter and lexicographically smaller words. The result is a clean and optimized solution to the problem. To solve this problem, we start with a basic example using the input words array, app, ap, apple, apply. The first step is to create a word underscore set from the input, which allows for quick lookup of any word or prefix. For this case, the word underscore set becomes app, ap, apple, apply. Next, we sort the words in ascending order based on length, and if two words have the same length, we sort them lexicographically. After sorting, the words become ap, app, apple, apply. Now, we iterate through each word in this sorted list. We initialize longest underscore word as an empty string. Starting with the word a, it has no prefixes, so it trivially satisfies the condition that all prefixes exist in the word underscore set. As a result, longest underscore word is updated to a. Next, we examine the word ap. Its only prefix is a, which exists in the word underscore set. Since all prefixes are valid, we update longest underscore word to ap. Moving to the word app, its prefixes are a and ap, both of which exist in the word underscore set. Again, all prefixes are valid, so we update longest underscore word to app. Then we consider the word apple, which has prefixes a, ap, and app. All of these prefixes are present in the word underscore set, so we update longest underscore word to apple. Finally, for the word apply, its prefixes are a, ap, and app, which also exist in the word underscore set. However, we skip updating longest underscore word because apply is not lexicographically smaller than apple, and both have the same prefix validity. Thus, the final output for this example is apple. Now let's look at another example where the input words are a, b, ab, abc. The first step is to create the word underscore set, which becomes a, b, ab, abc. Next, we sort the words by length and lexicographically, resulting in the same order, a, b, ab, abc. We initialize longest underscore word as an empty string. Starting with the word a, it has no prefixes, so all prefixes trivially exist, and we update longest underscore word to a. Next, we process the word b. While it has no prefixes and satisfies the condition, we skip updating longest underscore word because b is not longer than the current longest underscore word, which is a. Continuing with the word ab, its prefix is a, which exists in the word underscore set. Since all prefixes are valid, we update longest underscore word to ab. Finally, we examine the word abc. Its prefixes are a and ab, both of which exist in the word underscore set. All conditions are satisfied, so we update longest underscore word to abc. The final output for this example is abc. In this edge case, the input words are a, triple A. First, we create the word underscore set, which becomes a, triple A. Sorting the words by length and lexicographically results in the same order, a, triple A. We initialize longest underscore word as an empty string. Starting with the word a, it has no prefixes, meaning all prefixes exist, so we update longest underscore word to a. Next, we process the word aa. Its only prefix is a, which exists in the word underscore set. Since all prefixes are valid, we update longest underscore word to aa. Finally, we examine the word triple A. Its prefixes are a and aa, both of which exist in the word underscore set. All conditions are satisfied, so we update longest underscore word to triple A. The final output for this edge case is triple A. To understand the time complexity of this solution, we break it into three main steps. First, we create a set from the input list of words. This uses the set function, which processes each word once, resulting in a time complexity of O, n, where n is the total number of words in the input list. Next, we sort these words. The words.sort function sorts the list by length and lexicographical order, which is done in O, n*log, n, time. Sorting is a significant step because it ensures that shorter words are processed first, making the prefix checking logic efficient. Now, the third step involves iterating through the sorted list of words. For each word, we use a for loop, which contributes (n) to the time complexity since every word is visited exactly once. Within this loop, the all function checks whether all prefixes of the current word exist in the set. If the word has a length of k, this prefix check involves k1 iterations. Each lookup in the hash set is O1 on average, so checking all prefixes for a single word takes k time. Summing this across all words, the total time becomes sum k_i, where k_i is the length of each word. In the worst case, this sums up to n*m, where m is the maximum word length. Combining all steps, the overall time complexity is n plus n*log n plus n*m. Since n*log n dominates n, the total complexity simplifies to n*log n plus n*m. Analyzing the space complexity, we start with the word underscore set, which stores all unique words. If the average word length is k_average, the space required for this set is approximately n*k_average. Sorting the list is done in place using timsort, so it does not require additional space beyond the input list, contributing 1 auxiliary space. The longest underscore word variable, which keeps track of the result, uses m space, where m is the maximum word length. During the iteration, each prefix check uses string slicing. This creates new substrings in memory, leading to a total space usage of m for each word. Summing this across all words results in n*m for prefix checks. Therefore, the overall space complexity is n*k_average plus n*m, with the dominant factors being the storage of the word set in the memory used for prefix slicing. When considering the best, average, and worst cases, the time complexity varies based on input characteristics. In the best case, if most words are short or the all function fails early for many words, the prefix checks are minimal. Here, time complexity is closer to n*log n, dominated by sorting. In the average case, the prefix checks are more substantial, so the complexity becomes n*log n plus n*m, where both sorting and prefix validation contribute. In the worst case, where all words are valid and require full prefix checks, the complexity remains n*log n plus n*m, as every word undergoes maximum length prefix validation. The worst case scenario occurs when all prefixes exist, requiring the algorithm to check every possible prefix for every word. To highlight the efficiency of the optimized solution, let's compare it to a naive approach. In a naive solution, each word's prefixes are generated and checked against the entire list of words. This involves m prefix generation for each word, combined with n lookups per prefix. For n words, this results in a time complexity of n²*m. In contrast, the optimized approach leverages hash sets for 1 average time lookups. This reduces the prefix checking complexity to n*m. When combined with sorting, the total complexity becomes n*log n plus n*m, a significant improvement over the naive n²*m. Sorting dominates when words are shorter, while prefix checks dominate for longer words. This balance ensures an overall complexity of n*log n plus n*m, making the solution both time and space efficient. When tackling this problem, there are some common mistakes you'll want to avoid. First, ignoring prefix validation for all prefixes is a frequent error. Some assume that only the first few prefixes of a word need to exist in the list, but this is incorrect. Every prefix of the word needs to be checked to ensure the word meets the criteria. Skipping even one prefix can lead to false positives, which would invalidate your solution. Another mistake is using an inefficient method for checking if a prefix exists, such as relying on a list. Since list lookups typically require n time, this can lead to an overall time complexity of m*n, where m is the number of words and n is the average word length. Instead, using a hash set reduces lookup time to 1, making your solution significantly faster. Additionally, misunderstanding edge cases can be a pitfall. For example, you might overlook scenarios where the input includes edge cases like empty strings, single character words, or duplicates. These are common in interviews, and failing to address them can lead to incorrect results.
Lastly, processing words in an arbitrary order rather than sorting them by length is another mistake.
Longer words often depend on shorter ones, so sorting ensures that you validate prefixes in the correct order, leading to a more robust solution.
Another issue to watch out for is overcomplicating the prefix check.
Some solutions use nested loops or repeatedly slice strings to validate prefixes, which introduces unnecessary complexity. Instead, leveraging a tree or a hash set can make this process much simpler and more efficient. Now, from an interview perspective, it's important to recognize patterns. This problem centers on the concept of prefixes, which is a common theme in string manipulation questions. Be prepared to discuss the trade-offs between using tries and hash sets, as interviewers often probe your understanding of these data structures. Edge cases are another area of focus. You might be tested with inputs that are empty, extremely large, or contain words that are substrings of others. Showcasing an awareness of these scenarios will demonstrate your thoroughness. Optimization is also critical. While it's fine to start with a brute force solution, interviewers will expect you to refine it by incorporating more efficient data structures like tries or hash sets. Finally, remember that communication is key. Clearly explaining your approach for handling prefixes and justifying your choice of data structure can set you apart as a strong candidate. This problem is closely related to several other LeetCode questions that you might find helpful for practice. For example, LeetCode 208, Implement Tree, Prefix Tree, is directly relevant because it involves building and using a tree for prefix-related operations. Another useful problem is LeetCode 720, Longest Word in Dictionary, which also focuses on finding words based on prefix constraints. LeetCode 14, Longest Common Prefix, and LeetCode 139, Word Break, are also worth exploring as they involve similar string manipulation concepts. In terms of alternative approaches, there are three main strategies you can consider. Using a tree is one of the most efficient methods. You can insert all words into the tree and then validate each word by checking if all its prefixes exist in the tree. While this approach is fast, it does require more memory. Another option is to use a hash set for prefix validation. By storing all words in a hash set, you can quickly check if each prefix exists. This method is easier to implement and uses less memory than a tree, but it may be slower for validating very long words. Finally, sorting the words by their length and validating prefixes iteratively is another approach. This method adds overhead due to the sorting step, which has a time complexity of O and *log n, but it simplifies the validation logic and ensures prefixes are checked in the right order. Each of these approaches has its own trade-offs, so choose the one that best fits the problem constraints and your needs during an interview. Great job! Today, we explored the longest word with all prefixes problem. We discussed key insights and approaches to solve it. Keep practicing string and prefix-related problems to strengthen your skills. Thanks for watching, and see you next time. That's the end of this tutorial. I hope you found this explanation helpful for understanding the solution to this LeetCode problem. If you enjoyed this content, please consider subscribing to the channel for more coding tutorials and solutions. Feel free to leave a like if this video helped you, and don't hesitate to comment with any questions you might have. Thanks for watching, and happy coding!